symbol. Their end. And whenever he shows his hand, he can move the next
Professor.
page.
Yeah, Professor.
Yeah.
Yeah, Professor.
Okay.
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 Professor Barry, please send the file PPT if it
Oh.
is if you need to present from here. Okay. I think Nikhil said that it has not reached here.
Oh.
Or otherwise you can send present whatever. We are ready, Professor.
I don't. Usually, when I press to open a window, it shows all the windows that I have open, but it doesn't show the one that I want.
Is the file open on the window?
Yeah.
Oh.
We can't able to see it.
Would you please share it once again, Professor? Once again, try it once again.
Barry, can you send an email to Satish your file? He can open it from his end. It will be easier.
Oh, okay. All right, just let me get back to the.
Yeah.
Okay. Okay, Professor, let us try.
Actually, we have tried this.
Satish.
Okay.
Yeah, Professor. Yeah, Professor.
Barry got the file, it looks
Yeah,
like.
yeah.
Is that good for you?
Yeah, we have the file. No worries. He can put it on full screen for you.
Yeah.
Yeah. And just lift your arm and he knows that he has to switch to the next page, okay?
Okay.
Yeah.
Can you see that?
Yeah, we can see it. We can see it. Okay.
And see, I can
Everything
move
looks
the
good.
pages.
Yeah,
It's all set, guys. Finally.
Yeah.
Okay. Can you see and hear me?
Yeah.
Yes.
Okay. All right. Sorry, my apologies for not doing this so smoothly. So she's had me practice twice, and I did it great. But this time, when I looked for the windows, it didn't show up. The reason was I had too many windows open on my computer. After I shut down a bunch, I was able to do it. forget that though. Let's continue on. Thanks for the invitation. And so, in spirit, this is where I am. I'm going to talk about some joint work with the late B.G. Manjunath from Hyderabad and Sachin Sachdeva, who's been working with me for the last couple of years. For an abstract, proportional reversed hazard models are very useful in a lot of applications, especially with survival situations. And they're sort of a proportional reverse hazard family of distributions. We can show that they are effectively obtainable from a power function distribution family. And what we're going to talk about is rather than just the individual distributions, we'll talk about associated processes. So we're going to start out with the first observation. I said that they're related. The relationship is very simple. A proportional reverse hazard model involves a basic baseline distribution, usually denoted by F0 with a quantum function F0 inverse. And if you have a power function distribution process, Xn, the corresponding proportional reverse hazard process is just obtained by evaluating the quantum function evaluated at Xn. Okay, so we're going to be talking about almost completely about power function distribution processes, but keep in mind that most of the applications will be for these proportional reverse hazard models. So we'll begin by looking at proportional reverse hazard power function distribution process. And there are a couple that got us interested in this problem. One was introduced by Kundu, and his process was defined as follows. This thing is built out of a sequence of IID uniform 0-1 random variables. And we define the process Xn, where Xn is the maximum of two successive UNs, the current UN and the previous UN, raised to different powers. At this stage, let me remind you a couple of things about the relationship between the uniform distribution and the power function distribution. If you take a uniform random variable and raise it to the power 1 over alpha, then what you end up with is a distribution, a random variable which has a power function distribution with parameter alpha. And power function distributions are kind of neat, because if you take a power of a power function variable, it has a power function distribution also. And there's a second property that power function distributions have is, if you have two independent power function distributions with parameters, let's say alpha 1 and alpha 2, then the maximum has a distribution that is of a power function distribution form with parameter alpha 1 plus alpha 2. Now, this process that was introduced by Kundu is kind of interesting. The following statement, for each n, quite obviously, Xn has a power function distribution with parameter alpha plus beta, because un to the 1 over alpha is power function alpha, un minus 1 is power function beta, and they're independent, so the maximum is power function alpha plus beta. So that works out fine. The joint distribution is not very difficult to work out, but it is available in a nice form. But it's not a distribution that has a joint density. Okay, the distribution function is nice, but it's kind of a mixed random variable, sort of reminiscent to the case that arises in the Marshall-Olkin exponential, bivariate exponential. And now, Kundu, Debashish Kundu, right? He claimed that Xn is a stationary Markov process. My statement here is that I'm willing to admit that it's a stationary process, but I'm not willing to believe that it's a Markov process. And I'm not quite sure that it actually is it's xn has the same distribution as xn plus 1 and xn plus 2, but I'm not sure that xn minus 1, xn comma xn minus 1 has the same distribution as xn minus 1, xn minus 2. I don't think it qualifies as a stationary process. It has a stationarity property that the marginal distribution is always power function distribution. Let me see if I can explain those things. The first thing I already explained, we just used the fact that maximum, that u to a power is power function, v to a power is a power function, so the maximum is also, so that's easy. Distribution function, it's a little bit difficult to work out, but it's fairly straightforward. So I won't spend time on that, but it's available. Part C, stationarity is trivial if you say that x1 has the same distribution as x2 has the same distribution as x3. But I don't think that x1, x2 has the same distribution as x2, x3. Now, when we wanted to check to see if it really had a Markov property, we did the following. We looked at the distribution, or the distribution function of x3 given information about x2. And then we looked at the distribution of x3 given information not just about x2, but also about x1. Now, if it's a Markov chain, then these two things should be the same, because the future is supposed to, given the present, the future is independent of the past, and this information about x1 less than little x1 should not matter. But when we work the things out, okay, then we find that in fact they are different, and that then we look for a better argument for it. But there's actually in DeBus's paper, there was a key to observing why it's not a Markov process. He made the observation that with the definition that he has, if we're brave enough to go back to the original definition here, if you took 2xn and xn plus 2, okay, then they will not depend, then the two randomabilities will actually will be functions of independent uniform randomabilities, meaning that two x's that are separated by a space are independent. Now that's a curious property, and it's not only is it curious, but it just cannot happen in a Markov process. Okay, so when you have a Markov process, the individual x's are dependent. It's for the exception, of course, is if all the xi's are IID, but we're obviously not looking at that situation. Okay. Once you've recognized the Kondo process, the important thing to do is to look at the distribution property. The density of xn is fine. The joint density of xn minus 1 is not so nice, but the marginal density of x is just because it's a power function distribution. And then the moments, first and second moments, and any other moments you want are very easy to work out. The first thing you would think of relation. But if you're going to have to work that out, you've got the means and variances, but you'll need to evaluate the expected value of xn minus 1. It turns out to be a bit complicated. Here's the computation of it, and written in terms of three random variables, u, v, and w. Xn is the maximum of u and v, 2 powers, and xn minus 1 of v and w to certain powers. And when you write it out this way, there are 4 components. Be brave, look at the next page, and in many cases, conditioning on u, one of the u's, one either v or w or u, you can work the things out. and you end up with these four expressions. So I have not written down what the expected value of x1 times x2 is, because it's the sum of this, whoops, it's the sum of, I can't point at it, it's the sum of the four ugly expressions on this current slide. And if you can imagine, if you were going to use some kind of method of moments estimation, you could use means and variances, that would be fine, but they would not capture the dependence properties of the process. And if you try to factor in this horrible expression in a moment equation, then although it can be done, and some of my more talented friends are not perturbed by any kind of ugly equation. They say we can solve it if it has a solution. Well, we'll let them do it. Correlation is very complicated, but computable. But another way to look at dependence is to look at the fluctuation probability. What's the probability that x1 is less than x2, or that xn minus 1 is less than xn? Okay. This turns out to be, once again, coming back to the original definition, it turns out we have to break into two cases. If alpha is bigger than beta, conditioning on one of these variables, but conditioning on u1, and we work the thing through. And in the end, you get a very nice expression, alpha over 2 alpha plus beta. And if you remember, I said we had two cases. If alpha was bigger, if alpha was, that was if alpha was bigger than beta. If alpha was less than beta, we get a different expression, beta plus alpha or 2 beta plus alpha. But in either case, they'll be quite useful for method of moments estimation approaches to getting hold of the parameter estimates without just using marginal information. In fact, we talked, remember, about these proportional reversed hazard processes. DeBessis-Condu actually looked at a particular choice of this where F0 was a generalized exponential distribution. And I would like to remark that I've done quite a bit of work with Pareto distributions. And if you have a power function distribution, it's reciprocal as a Pareto distribution. So effectively, we could recast the discussion throughout this paper or this presentation in terms of Pareto processes, which are particularly useful in socioeconomic data analysis situations. So that may be the things that DeBessis was thinking of was applications in reliability settings, but we could also have applications in these socioeconomic situations. Well, we were a little bit unhappy with the non-Markovian nature of the Condu process. So we thought we'll try to come up with an alternative power function distribution that would not have this problem. Okay. I remember I told you about the key properties of the power function distribution. If you had a couple of independent power function variables, then the maximum also had a power function distribution. And there was also the fact that if you took a power of a power function variable, it had a power function distribution also. Okay, well, we can use those observations to define an alternative, and this will be a stationary power function distribution process. It's going to have power function distribution marginals with parameter alpha, and it is going to be a Markov process by its construction. We define x0 to be a uniform random variable raised to the power of 1 over alpha, which of course has a power function distribution. And for the subsequent ones, the nth xn is the maximum of the n minus first raised to the power alpha over alpha minus delta, and an independent uniform random variable raised to the power of 1 over delta, where delta is between 0 and alpha for things to make sense. and the UNs or IID uniform random variables. It's not difficult to verify that this process is completely stationary, and with each xn having a power function distribution with parameter alpha. Okay. To work through that, right, to make sure that given that to make sure that xn has a power function distribution, we have to go through the argument that xn minus 1 being a power function random variable is actually a power of a uniform random variable, and then it's been raised to another power. So this is a power of a uniform random variable, and this is a power of an independent uniform random variable. And if you look at the so whatever that power is, a uniform random variable to 1 over the reciprocal of that is a power function distribution, and so they add up perfectly. Each time I look at this thing, it looks kind of strange, but you check me out on it. This thing really is a stationary process. It's an example of what's often called the innovation process, or what's called a maximization process, or a maxification process, parallel to minification process, which are quite common in the literature. The minification process are of the form a constant times the minimum of xn minus 1 and an innovation random variable yn. And what we have here is a maximification process. I don't know if anyone's used that name before. It is a Markov chain. It's stationary. It has a long-run distribution that's power function distribution alpha, a stationary distribution that's of that form. I came up with some, rather Sachin came up with some pictures of successive realizations. And you see with the first 10 observations, they're really rather wildly, these are 3 different realizations, and they can move around quite a bit. Remember, the range of these variables are all between 0 and 1. It gets even more exciting when you look at 100, a time series of length 100, but it's squeezed in together there to just fit in this picture, which makes it even look more erratic than it really is. Okay. So the observation that we've just made, it is a stationary Markov process. It has power function distribution with parameter alpha as it's for each n, and the joint distribution function is actually even easier to work out than the one that for the undo process. And again, this is the verification that I said that you might wonder about whether this thing really is has a power function distribution with parameter alpha, and it's the max. So the first one has to be less than x, and un minus has to be less than or equal to x. And these are 2 independent random variables, so we break it up that way. This one is that xn is less than or equal to x to a power, x to the delta, and finally we end up with the result that we want, x to the alpha. So, and by induction, you can get it for the entire process. The joint distribution, again, I'm not going to go into all the details, but it's relatively straightforward again. If we want to look at distributional properties, since it is a power function distribution, the marginal densities, simple. First and second moments are simple. If we were looking at the correlation, hoping that would be nicer than the Kondo correlation, well, the expected value of x0, x1 is not as ugly as the expression for the Kondo process, but it's still kind of a mess. And so in this case also, well, here's the covariance. one thing you can do is with this function, you can convince yourself that the correlation is a decreasing function of delta. Delta is between 0 and alpha, remember that. If with that sequence is of our kind, then we claim that the step up or the step down probably that x1 is less than x0. In other words, that the process has decreased is alpha over alpha plus delta. And for this one too, what you need to do is condition on u0. And it comes out pretty nicely. Now, once we thought about that, we thought about the possibility of looking at second order processes, because there should be the possibility, if you have first order processes in applications, it's quite frequently the case for Markov processes that you have dependence that goes back more than one time unit. And so we thought that we should be able to come up with a nice second order Kondo process. And it turns out that's really quite easy to do. We just take xn to be the maximum of the current innovation variable to a power, and the two previous ones to a power. We take the maximum of those two. And if you work that thing out, using our knowledge of the fact that a uniform variable to a power 1 over alpha has a power distribution with parameter alpha, and maxima of independent power function distributions also have power function distributions. So xn has this with parameter alpha 0, alpha plus alpha 1 plus alpha 2. And then that means, of course, that we can write down the density of xn and the mean and the variance very easily. So that's going good. If we want to get the second moment for this, it was bad enough in the first order process. We could expect it to be even worse in the second order process. We have not been able to make much progress on that. Okay. In parallel fashion, you could always think about a kth order Kondo process where you just have the xn depend on the previous k times, as well as so that it's today's innovation and the previous k innovations. And there's a reverse second order Kondo process, which has different distributional processes, which could be kept in your toolbox for certain other distributions, which have more complicated dependence than a simple Markov chain dependence. Okay. And it would be desirable to conduct a second order version of such processes based upon a suitable sequence of IID uniform random variables. Remember, this is the alternative process. Remember, it had a more complicated definition. And it looks like you should have xn being the maximum of xn to a power, xn minus 2 to a power, xn minus 1 to a power, and un, the innovation variable, to a power. We just have not had any luck with that. It intrigued us, and I've spent more time on it than I should have. And Sachin, I think, has given up on it too. It's going to have a lot of changes. Well, if we want to do some parameter estimation for some of the processes that we've looked at, the Kondo process and the alternative power function process, remember that because we don't have bivariate joint densities, that means that likelihood-based inference will have to be rather creative if you're going to pull it off. And Bayesian inference is going to be particularly challenging because Bayesians like to have a prior density, a likelihood density, and to get a posterior density, and they always think that that's the final solution to most problems. But it requires that you have densities. What we do is use a method of moments approach for a sample of the first m x's. We look at the average of the first m and the proportion of them for which xi is less than xi minus 1. And then we can equate those to the expected values in this fashion. And when you do that, you get a very simple analytic expression for the estimates in this situation. Now, if we wanted to do the same kind of thing for the alternative power function distribution, then we would look at the expected value of xn, which is going to be alpha over alpha plus 1. And we have the probability that x1 is less than x0 is alpha over alpha plus delta. And we solve those equations and we get a very nice, analytic, simple estimate of the two parameters alpha and delta. The moment-based estimates that we presented are consistent because they follow from the fact that, not the fact that the estimates are continuous invertible functions of statistics that converge almost surely to their expectations. So that's a very simple argument to conclude that these estimates are not just consistent, but they're strongly consistent. I think I've gone through too fast, but that's okay because I got started very late. Key references. If you want to see more about Pareto process, the reference number 2 by myself, and for other minification processes discussed in 3. And further down, of course, the important reference to Devassis-Kondu. There are a couple of them. One is a stationary generalized exponential processes, and then he looked at some bivariate models with proportional reversed hazard marginals, which is sort of a rather than looking at a process, it's just looking at two successive random variables in the process. And finally, I guess that's it. And thank you for your attention. I had a timer that I had set that was going to time myself, but in the excitement of trying to get this thing started, I didn't set it. So
yeah, it is in time, no problem, Professor. Just a few minutes only.
Thank you, Professor
Thank
Barry Arnold, for the nice talk.
Thank you. I forgot to show. This is my hometown. Join me on the beach. And again, thank you.
Okay. Any questions from the audience? Professor Balakrishna may be having some questions.
I have not a question, but more of an inquiry.
Okay.
I noticed that both the original Sachin is also in the audience. Barry, I don't know whether you noticed. Sachin is here too. So
is Sachin here? Okay.
Yeah,
Well,
he's also here. Yeah.
I hope I didn't say anything wrong about him.
Yeah. First, one observation. In both the original process and the new process, it looks like it is always under-dispersed. Because of the nature of the power function distribution, the variance is always smaller than the mean. Is this something that is always desirable, or is there a version that you can construct where you can also have over-dispersion in the model?
I think your key observation that it's a property of the power function distribution.
Power function distribution. Correct.
Yeah, that's what really does the problem. It's a random variable bounded between 0 and 1, and by its very nature, as you observe, you have under dispersion.
Under dispersion. Okay.
Yeah, and the only way you could do that, you could switch over by taking reciprocals, switch to a Pareto process, and then you'd have over dispersion.
Correct.
But I don't see that I can sort of paste the two together to have both things, or to have a model which sometimes is under dispersed, sometimes over dispersed. Although I would agree that would be a very good thing to find.
Yeah, because from the data, you can identify whether under dispersed model is reasonable or over dispersed model is reasonable, because it's just based on the mean and the variance. One can use a index of dispersion. That's one. But the second one is a more subtle point. Barry will remember that there is an analog in the case of discrete order statistics. While the discrete order statistics do not form Markov chain, but if you take a bivariate pair where you look at the order statistic and the number of ties, then they form a Markov chain. So here, the connection is, if you look at the basic construction, you are taking the maximum of two random variables, let us say. But suppose you start with U0 and U1. So you take a maximum of a power of U0 and a power of U1. Can we create an indicator vector? The indicator vector should tell which one of the components gives rise to the observation. So, for example, it will be 1, 0, 0, 1. It cannot be equal, so you can't have 1, 1. So, if we create a bivariate indicator indicating which variable is giving rise to the underlying sequence, whether that will throw some additional insights or information into your calculations.
That would, but the usual assumption would be is that all you observe is xn. Those UNs, they're hidden in the background. You know, God knows what they are, but we don't. We know that somewhere he has taken maxima, and but we don't have the option of seeing those.
Yeah.
It would be a different process.
Yeah, but if the indicator variables probability distribution or something determined, then they can be treated as latent quantities in the maximum likelihood estimation. Some EM algorithm could be used, for example, in addition to identifying some distributional properties.
Well, it sounds interesting. I'm not sure I see how to do it off the top, but it's going off in a new direction. And as usual, I expect you, Bala, to suggest that I should go in a new direction.
No, nothing like that. It's just that a thought that I thought might be useful even for inferential purposes. You observe only the sequence xn, but you do not know which gave rise to xn. So that's like a latent variable you can use. That was my idea.
Okay, that's interesting. I hadn't because they certainly, the process is certainly defined in the key construction. It starts with that IID uniform sequence,
right?
And it's not available for us to see, but it could be something that we could try to. But there's so many of them.
True.
It's 10 o'clock.
Yeah.
Perfect.
Okay.
Thank you.
Thank you, Bala. I always count on your counsel and your good suggestions.
Well, we both are old. Sachin is young. He can do it.
Yes, sir. I certainly know. I have noted it down.
Yeah, okay, good.
Yes, sir.
Sir, I have a doubt. Can I?
Sure.
Sir, it's something like an observation that you may clarify. Initially we start with uniform 0, 1. Is it always necessary that it should be 0, 1, or can it be something like 0, comma some other constant? And in particular, I will complete my question. In particular, why I am asking this question is, if that in the uniform distribution range itself, somehow if you are able to accommodate alpha or 1 by alpha, something of that sort, any of the subsequent issues that we are discussing about, could it be addressed?
Well, of course, you could just a uniform 0 gamma is just gamma times a uniform 0, 1. So that if that's appropriate for your modeling purposes, I think it's actually the power function process being restricted to 0, 1. It's very restrictive, and a lot of data that you collect will not be of that type. But often it can be transformed into variables that are between 0 and 1, and then you might find application for power function processes there. But there are lots of other processes bounded on the interval 0, 1, so you can only do so much with this model. One of the proportional reversed hazard model, if you chose an F0 that just had support 0, 1, then you by that end up with a proportional reversed hazard model that also is bounded between 0 and 1, and perfectly valid one if you want, if that makes sense for your data. You could always add more structure to the model. You could embed this model in a much more complicated model. And again, that should be driven to some extent by possible applications.
Thank you, Professor. Thank you for your clarifications.
Thank you for giving me the alternative, and I really do apologize for the problems that I had getting started. Even after practicing twice, I couldn't do it. But I've learned something. If I want to do this next time, to shut down almost all the windows that I have. And then I'd have no trouble.
If there are no more questions, let us thank the Professor Barry Arnold for his talk.
Okay. Again, I thank you for your attention.
Thanks. Bye.
Bye. Hannah, please conclude the
Yes,
session.
sir. Yes, sir. On behalf of the organizing committee of WSTA 2026, I extend my sincere thanks to our respected session chair, Professor David Hanagel, for chairing this session. I also express my heartfelt gratitude to our distinguished keynote speaker, Professor Barry C. Arnold, for delivering an inspiring and insightful keynote lecture on some power function distribution processes. Thank you for sharing your valuable knowledge and research insights with us. We truly appreciate your time and contribution. Thank you all.
I did not know that Professor Manjunath passed away.
Okay.
Yes, sir. Unfortunately,
Yeah.
December 2024.
Oh, okay.
That's 2 years ago, I think.
Yeah, only when I saw late Manjunath in Barry's presentation, I realized he passed away. Must have been recent, I thought.
Yes, he was my supervisor in Hyderabad.
Yes, I know. Yeah, I have seen your work. Sorry to hear this news. Yeah. Mhm.
Yes, sir.
Please do keep in touch.
Yes, sir.
Okay.
Thank you, sir.
Take care, Barry. I will talk to you when I return to Canada.
Okay. Hey, Bala, sorry I missed your party.
Oh, that's okay. No problem. But your video was played on the opening ceremony.
Oh,
Okay.
good.
I will talk to you when I return home, okay?
Okay, fine.
All right. Okay. Bye-bye. Take
Bye.
care.
Bye-bye.
Bye. Bye.
Devika, please move to the next. Yeah.
Yes, sir. Good morning, everyone.
A warm welcome to all of you to Technical Session 11, Plenary Session of WSTA 2026. It is my pleasure to introduce our session chair, Dr. K. Kandamare Kanni. Sorry, it is my pleasure to introduce our session chair, Dr. K. Kandamare Kannan. Dr. K. Kandamare Kannan is a highly distinguished academician and senior professor in the Department of Statistics at Manomandan Sundaranath University in Tirunelveli, Tamil Nadu. With over 3 decades of profound experience in higher education and statistical research, he has significantly advanced the field of data sciences and served in critical university leadership positions. A highly decorated researcher, he is a recipient of UGC BSR one-time grant and Tamil Nadu Young Scientist Award. I now introduce our speakers for the session. Our first speaker, Dr. Carlos Coelho, Professor, University of London, who will present on a generalized Taylor Pareto distribution sharp approximation for this PDF and series. Our second speaker is Professor David Hannibal, Savitribai Philip Pune University, who will present modeling kidney infection data using compound geometric shared probability models based on additive hazard. We look forward to an informative and engaging section. I now respectfully invite Dr. Sandamare Kannan to kindly chair the section and commence the proceedings. Over to you, sir.
Professor Sandavakandan, there is whether you have mobile and laptop, one of the audio you can stop, Professor, so that will work. Professor, unmute your mic, Professor. Unmute your mic.
Is it okay now?
Yeah. Okay. Professor, it is okay, but whether there is both mobile and laptop audios are on. Yeah, one of them can switch off. One of the audio switch off. Yeah. Then it will.
Okay, Professor.
Yeah, okay, Professor. Okay, Professor.
It is very good morning. It is a great pleasure. Very good morning to Professor Satish Kumar and his team. He is very fantastically organizing 11th hybrid international webinar on recent trends in statistical theory and its applications. It is a great opportunity to given him for the entire team. Now it is a great opportunity to introduce Professor Carlos. He is a full professor of statistics at the mathematics department of Nova School of Science and Technology of Nova University. He holds PhD in biostatistics by the University of Mexico, where he was a Fulbrighter. His main area of research in multivariate analysis. Other areas of interest related with this area are mathematical statistics and distribution theory, as well as estimation, univariate and multivariate, linear, generalized linear, and mixed models, and more recently, also tests for higher dimensionality cases and the application of multivariate analysis techniques of statistical disclosure control problems. Carlos has served as associate editor in the editorial board in several journals, in reputed journals, as well as he is the board of the Journal of Statistical Theory and Practice editorial board, the American Journal of Mathematical and Management Sciences, and discussions mathematics, probability, and statistics, and an associate editor of Springer book series Emerging Topics in Statistics and Biostatistics, and is a member of the International Council of the Business World Library of Academy of Economics. Currently, Carlos also serves as Vice President of the Portugal Fulbright Alumni Association. In this great person, I invite to his talk in the eminent audience. Please, Professor Carlos, kindly spare your valuable time.
Professor, welcome, Professor, please.
Thank you very much. I really appreciate it, and I thank and I really want to thank very much the introduction, very nice presentation that you did of me, and thank Professor Satish Kumar for inviting me for this conference. So let me see if I can share my presentation. I'm having a small problem, just like Professor Mary Arnold, but I think you can see my screen now. Can you? Okay, so let me see.
Not at
if this will work well. Can you see my screen now?
Not at present. Please, can share it once again.
I always have a problem in. Okay, let me see if it will work now.
Yeah, now it is okay. Now it is coming. You can see the desktop. Yeah, now the screen. Okay, it's fine.
It's okay now. Oh, okay. Thank you very much. So once again, thank you very much for inviting me, and I'll be doing a presentation on a distribution for which it is not really possible to obtain an explicit form for the PDF or for CDF. But so let me say a little bit more precisely what we are after. So in his book, Feller, in his second volume in 1971, he defined a Pareto distribution, a very peculiar one, as being the distribution of the random variable U that is equal to 1 over y minus 1, where y has a beta distribution. And then Barry Arnold, in his 2015 book, he called a Feller-Pareto distribution, the distribution of this x random variable that is equal to sigma. Sigma is some positive value, sigma times 1 over y minus 1 raised to some power gamma. This gamma power is usually seen as being a positive value also. And so the random variable x has the same distribution, we can show it rather easily, as y1 over y2 raised to some power gamma, where y1 and y2 are independent gamma random variables. This model, Feller-Pareto distribution, is a rather well-known family that is indeed a generalization of Pareto for a family of distributions, and as such, it has a lot of applications in economy and in social work. The PDF of X is rather simple to really be obtained, and it has a rather simple expression. CDF may be also obtained in the closed form, although we should use some special functions for that. But what I propose here, it is really to obtain the distribution of a generalization of this random variable that would be a random variable with the same distribution as y1 power gamma 1 over y2 power gamma 2, where gamma 1 and gamma 2 are different. Moreover, we'll be assuming that they may be either positive or negative, but different yet. What happens it is such a random variable does not have an explicit closed form for the PDF or the CDF. And so we should really find some some sharp approximations. At first, we'll be finding an asymptotic approximation for the distribution. We will see the approximation is not all that good, and then we'll be developing what we call a near exact approximation. Why doing this? Well, two main reasons. One of them, it is a good challenge. Second one, the process we'll be using may be actually used in other situations. For example, if instead of considering the ratio, as it will be the case in my presentation, we may want to consider the product of the variables. Just for convenience, we'll be denoting each one of the 1 over gamma I as being beta I, because as we'll see next, it will be a bit easier dealing with the beta i's than with the gamma i's. So let us just settle down some notation as a start. We'll say that the X random variable has a gamma distribution with the parameters R and lambda. R is the shape and lambda the rate. If the PDF is that one that is above there. I'm not sure you can see my on my screen if you can see the cursor, but I hope. Then we'll say that the random variable y equal to the power 1 over beta of x, it means x to the power 1 over beta, it will have what we call a generalized gamma distribution. Here we will be assuming that beta may be any real value that not zero. It means it may be either positive or negative, but not null. If it would be null, it would not make much sense. Then we will denote y as having a generalized gamma distribution with parameters r, lambda, and beta. Beta is the power parameter. So let us now consider y1 and y2. They will be independent random variables, and each one of them will be a generalized gamma, with the two betas being different, but either both being greater than 0 or smaller than 0. Because in case we have them with different signs, then we will be in the case of actually a product and not a ratio. Because then we'll be interested in the distribution of the random variable z, where z is equal to y1 over y2. What happens it is, as I said before, we cannot obtain a closed form expression for either the PDF or the CDF of z. And then what we will be doing, it will be, in the first step, we will be getting an asymptotic approximation, and then what we call an inexact one. In doing this, we will also obtain approximations, not closed forms, but approximations for a couple of integrals for which we cannot have an explicit and analytical solution. Okay, we'll be using this an indirect method, because if we try to use the common method of obtaining the PDF or CDF of a ratio of a couple of random variables, the two integrals don't have an explicit solution. So we should go around and work out a method a different way. That method will be using the characteristic function of the logarithm of z. But so first we need a couple of results. We know that if x is a gamma r lambda random variable, the h moment of x has this expression where h does not need to be integer, neither positive. We just need to have h larger than minus r, and r is a positive value. And then we can easily get from this expression the expression for the h moment of y, where y is the generalized gamma random variable. And so y is the power 1 over beta of x, and so we can get the h moment of y directly from the h moment of x with this expression here. And then from this last expression, it will be rather easy to get the expression for the h moment of z, because z is equal to y1 over y2, or otherwise it is equal to y1 times y2 power minus 1, y1 and y2 are independent, and so the h moment of z may be obtained from the h moments of y1 and y2 from the above expression over there. And it will have this expression, which is valid for h over beta 2 smaller than r2, or h over beta 1 larger than minus r1. But then what is interesting and very useful for us, it is that if we consider the logarithm of z, then what happens it is we can easily get an expression for the characteristic function of w, because by definition it will be the expected value of e to the power itw, and w is log of z, and so this is the expected value of z to the power it. I is the square root of -1, and t is any real value. What happens it is we can just use the above expression of the h moment of z, because in that expression h is actually defined in a neighborhood of 0. It means h may be 0 or maybe in some area below and also above 0. That is allowing us to replace it by it in this expression of the characteristic function. And so the characteristic function of w, it is just the above expression for the h moment of z, replacing h by it, or otherwise actually by 1 over beta 1 or 1 over beta 2 it. But it is actually just replacing h by it. Then what happens it is from this expression we cannot do much as it is in this form, but we can to just simplify a little bit the expression. It is to get rid of that last part you see there on the right hand side. We can work with the random variable w star instead of w, where w star is w minus k. This k is not a random variable. It maybe I should have used a small letter and not a capital letter. This k is not a random variable. It is this value here, and it is a real value. And then the characteristic function of w star is a bit simpler. It means it is the characteristic function of w that we saw before there, without that other part that we just had on the right hand side. And so it is only the product of the two ratios of gamma functions. Okay, then in each one of these gamma functions we can use the Euler product formula, or the gamma product formula, that is this one here, where this small gamma, it is the Euler constant. And then we can rewrite the characteristic function of w star using this expression on each one of these four gamma functions. We can rewrite it in this form here. Okay, what happens is we can still rewrite it once again from the expression above. We can multiply each one of the ratios by beta 1 or beta 2, and you get it in this form here, which is exactly equivalent to the upper one. But then we can still rewrite it, because what happens it is the betas, as I said before, they may be either positive or negative, and in case they are negative, we just need to go through a rewriting of this expression, where each beta star is the absolute value of the corresponding beta, and where the t star is actually equal to the sine of beta I times t. I may be 1 or 2, because as I said before, in this situation we are considering either the two of them are really positive or the two of them are negative. And so the sine of beta 1 and beta 2 is exactly the same. And so the t star is the t from the expression above times the sine of beta I. Then, if you look at this last expression, we can see it is the characteristic function of a sum of differences of independent exponential random variables, because this part here, each one of these products here, it is the characteristic function of an exponential random variable. And so here we just have here actually on the right hand side it is the exponential random variable with a plus sign, and on the left part it is an exponential variable with a negative sign. It means this is the characteristic function of an infinite number of differences of two independent exponential random variables. There are some shifts. Shifts are not that much of a problem. That is, in this first difference here, there is a shift there that is the exponent of that exponential there. And then for each one of the other differences, there is a shift that is the exponent of this exponential here. Shifts are not a problem. We can deal with them, and you can apply them at the very end after figuring out the expression for the distribution there. As an asymptotic approximation, we just suggest what is more or less obvious, that is just going back in this expression, instead of using infinity, I just use some integer value there. And so the larger this m value will be, the better will be the approximation. And so this is now the characteristic function of a sum of m plus 1, m here plus 1 there, m plus 1 independent differences of two independent exponential distribution. Just for convenience of notation, we'll be calling Lk and nu k to these parameters here. And so if the betas are larger than 0, the expressions will be on the upper row. If the betas are smaller than 0, the expressions will be in this other down here. And so we'll be calling Lk and nu k these parameters here. And so now we can look at the distribution as being actually the difference of two independent sums of independent exponential distributions. And so what happens it is, for this, we just got an expression in that paper there. This is a reedition of a paper from 2007, actually. And on this paper, there are expressions for these differences of two sums of independent exponential distributions. And so from that paper, the PDF of W star and CDF of W star may be written in this way, where all these K's, K1, K2, there is a comma there that is spurious, there should be no comma. The K1, K2, the H1K, H2K, CK, DK, they are all defined in the next slide. And of course, you don't have to fix all these expressions, but they are defined here, okay? And the case, I'm really missing the definition for this case. These cases are just the product of the R from the independent exponential distributions. Okay, and so these HK, C are defined in this way. All this is finite and defined. And so we just have in this slide here, the PDF and CDF. These are the asymptotic ones because I am using their M instead of infinite. And so these are the asymptotic PDF and CDF of W star. W star is only a shift of W. And so we can get the PDF and the CDF of W. W is W star minus K from the PDF and CDF of W star. Sorry, W is W star plus K, where K is this real value as it was before. And then from the PDF and the CDF of W, we can easily get the PDF and CDF of Z. All these are asymptotic, and the approximations, as we will see next, are somehow good, but not all that good actually. And so what happens it is, in looking for a better approximation, we can use, instead of the asymptotic approximation, we can use what we call a near exact approximation. What is it? That is an approximation that in very beginning, this part here, the two first rows are actually the asymptotic approximation that was before there. And then we just add this other part here because we can show that any sum of differences of independent exponentials, it is actually a mixture of differences of exponentials. And so from that result, that is actually in that 2025 paper I mentioned, we can rewrite the characteristic function of W star in this way. We'll be calling this a near exact characteristic function because the upper part is a part of the exact one, and this summation is the approximation part. The approximation will be done in such a way that these weights, the PL weights, are computed in a way that the exact characteristic function and this approximate one of W star, they can actually match the first M W star minus 1. M W star is that integer value, the upper limit of the summation, that the distribution can match the first M double star minus 1 exact moment of W star, and then the last weight will be obtained as 1 minus summation of the other weights. This way, we can close CDF so that the CDF attains actually the value of 1. We claim that the near exact approximation we get here, it is much better. It means it is actually giving much better approximations to the exact distribution than the asymptotic representation we saw before. In a moment, we'll be getting some numbers that are showing well that the near exact approximation is actually giving a much better approximation. Another way we can really compute the weights, that is actually the one we just use in practice. It is saying that we can rewrite the near exact characteristic function of W star in this way, and then we can just compute the weights in this other equivalent way, which is a much more workable one, where this part of the characteristic function, this is a part of the characteristic function up there that is this part only. And so we can only get derivatives of this part, which is a much easier thing than getting derivatives of the whole characteristic function. And so, as I said before, this near exact distribution will equate, it will match the first M double star minus 1 exact moments of W. The PDF and CDF have a little bit more complicated expressions than the asymptotic ones, but the base that is inside the summations, it is actually similar to what was the PDF and the asymptotic PDF and CDF. What they have more, it is now a summation of several of these terms times those weights, the PL weights, which were obtained by equating the exact moments of W star and of W. And so all these parameters, K, H, C, and D, they are redefined, but the expressions are actually similar to the ones we saw before, where now the LJ and the new J just have a last one of the terms, a last one of their elements, say, which is a function of M star and L, because it is defined in this way. All the other ones back of these are actually defined in exactly the same way as they were defined before. But so each one of these sets has now one more parameter that is a function of M star. M star is the number of exact terms in the characteristic function, and also a function of L. L is this index that is going from 1 to M double star. Just showing some plots. These are the plots of the histogram. The red part, it is the histogram histogram of 1 million of a pseudo-random sample of size 1 million for one case. That is the case where the parameters for the generalized gammas are these ones here, R1, R2, lambda 1, lambda 2, beta 1, beta 2. This is just an example. And so the distribution is quite asymmetric. And so that part, it is the histogram of the pseudo-random sample. And the blue lines you see there are the representations for the asymptotic PDFs with m equal to 20, m equal 50. They are not that much far apart. The m equal 20 is actually the upper one that is a bit further away from the histogram. M equal 50, it is the inner one that is a bit closer to the histogram. But if we want to represent the PDFs with m equal 30 and m equal 50, you can see that they are almost on top of each other. It means as we just progress in this value of m, the approximations are getting better, but after some values, they are very, very close. If you just plot CDFs, they don't look even closer yet. And so here we cannot see the difference, but I have the CDFs, the asymptotic CDFs for m equal 20 and m equal 50. And so if we look at these plots, it looks like the agreement between the asymptotic distributions and the real one, it is really quite close. And it is really quite close, but not that much actually. We can use this measure. This is a measure I have been using for some time that really gives a very sharp upper bound on the difference between the exact CDF and the approximate one. The approximate one may be an asymptotic, or it may be a near exact one. But so you can say, but how can you measure that if you don't have an expression for the exact CDF? Yeah, that is true. But we just have the expression for the exact characteristic function. And so we can really compute this measure from the expressions of the exact characteristic function which we have, and it may be the near exact or the asymptotic one. Okay? And then this may be computed using a very good software, a software that has a very good module for numerical integration. And for example, Mathematica does the job in a very good way. But you need a specific software really. Then we can really compute these measures for the asymptotic distributions. For example, for m equal 20, 30, 40, 50, you can see as m grows, the value of delta goes down. I just had here delta 2, but it is delta. It is that delta there. This delta 2 is that delta there. And so as the value of m increases, the value of delta goes down, which is good. It means the distance, because this delta is a distance between the exact and the approximate distribution. So the approximation is better because the difference goes down. It means, for example, for m equal 50, the difference between the exact and the asymptotic CDF will be less than this value. And so this is a good enough approximation. But in case we just want to get it better, we can also compute the values of delta for near exact distributions. What I'm doing it is I fix the value of m star plus m double star. Here, this sum is equal to 30. And then I am researching what kind of combinations of values of m star and m double star give the very best approximation for a given sum of these two. And what happens, it is always when m star and m double star are equal that the approximation is better. Because, for example, here, if they are both equal to 15, the upper bound on the difference between the exact and the near exact CDF is this value here, which is lower than any other of the other values around. And then what we see, it is in case, because it is more expensive in computer time to really compute a large number of M double star moments, then we can go down here a bit. And so if you keep M star large enough, and if you have M double star large enough, we can still get very good values for the approximation. Let me show you the case where this sum M star plus M double star is equal to 40. In this situation, of course, the approximation is even better. Once again, the best case is when M star and M double star are equal. And so the approximation is here much better. And a little bit less good, say, it is if we lower a bit M double star and we keep M star high. And so the combinations, the good ones are if they are both equal. But for example, in case it may be a bit more expensive in computer time computing these many moments of the exact distribution, I can lower it a bit and I don't lose much in the approximation. Actually, the best result is for M star equal to M double star, because we can show that in this situation, it is the situation where we get a larger number of differences of two independent exponentials approximating the distribution of Z. As a byproduct, what happens it is, so why I'm going around with all these and I did not use the common way of getting the PDF, for example, of Z. That is what I said at very beginning, because in doing that, I'm stuck with two integrals that have no solution, no analytical solution. The two integrals, and so the distribution is very easy to really obtain if the two betas, beta 1 and beta 2, are equal, but we are in a situation where we want to deal with a situation where they are different. And so if they are different, any one of these two integrals does not have a closed form analytical solution. But so what happens it is that anyway, we found sharp approximations for the PDF of Z. It means that from the above results, we can actually get very sharp approximations for the integrals. It means that going through the statistics area, we can get very sharp approximations for an analytical, analytical result for a result in analysis, because this is an integral. And so we can get as a byproduct for this integral and for that other one, these approximations. The two of them, they came from the asymptotic PDFs of Z, and even sharper ones, we can get these that are actually coming out of the near exact approximations for the PDFs of Z. And so it means if you go through some kind of techniques usually related with the characteristic function of the random variable of interest or its logarithm, you can even get very nice results in the area of analysis actually, and not only in the area of statistics. Okay, just as a side note, as I said before, if the two betas, beta 1 and beta 2, they are equal, then the two integrals do have an analytical simple solution. Okay, but so I hope in doing this, I was able to show you a sharp technique to go through some situations where getting the exact expressions for the PDF or CDF of a distribution are very hard. And so we can still go around arranging the distribution, arranging the characteristic function of the random variable, or sometimes, as it was the case here, of its logarithm. And then we can even get side results that are somewhat nice in the area, not the statistics area, but in the analysis area, actually, mathematical analysis area. Just showing you for these integrals, I'm not sure how am I doing with time. Do I still have some time?
Professor, already time is over, please.
Okay, so
please.
just very quickly show you that we can get sharp results for those integrals. The exact value is this one for that integral with those r and lambda values. And so we just get the exact value just doing some numerical integration. And then the approximations coming out of the asymptotic approximation are these. This is the number of exact digits that are matched. But if instead we just use the near exact approximation, then we can get much sharper results with this number of exact digits matched. And so the near exact approximation, even for the integrals, is really giving a very sharp approximation to those integrals in the analysis area. And so this was what I really had to show you.
Thank you very much, Professor. You have given a wonderful talk. Now, I request only one or two participants interact with the Professor Carolus. Please. The time is very short. Those who are all interested, you please interact with one or two query to Professor Carolus.
Am I audible, sir?
Yes, sir. Yes, sir. Sachin.
So, Professor, sir, actually, I wanted to know, is this paper published? Can we have this paper? Because I wanted to read this paper more.
It is not really published. And this is not published. And this is a work that I really intend to say finished, because there are some points that are not done yet. Professor Barry Arnold will be visiting me in September this year. And so then we just intend to finish it and most likely write it as a paper, really.
Sir, I have one doubt.
Please.
Sir, Sir, most of the derivations and things, they are based upon the fact that beta 1 and beta 2 are of the same sign.
Yes, it is true. Exactly.
Yeah. Okay. From analysis and mathematical derivation point of view, that's okay. But is there any justification from the application end, or do you have any practical things that make this restriction meaningful?
It is because, just let me go to the very beginning. If they have the same sign, because we wrote z in this way, if they really have the same sign, it is a ratio, okay? But if they have different signs, it will be a product, actually, right? Okay. And so for that case, with the different signs, we can go in a similar way, but then the result will be quite different, because it will be just a sum of exponentials. But that is the case I was not addressing here, because if they have the same sign, this will be a ratio, because this is like something like this, okay? And so my are 1 over gamma. It means if the sign is the same, this is a ratio. If the signs are actually different, this is a product of two generalized gammas. And so that is the reason why I kept the two betas we did something.
Thank you, Professor, for your time and explanation.
Thank you very much for our Professor Carolus. We give you a wonderful idea regarding the youngsters and all researchers. On behalf of the organizing committee, we should appreciate your valuable time. Thank you very much, Professor. Now,
thank you very much.
Now we invite Professor David Hangel. Professor David Hangel is currently working as the Emeritus Professor, SP University of Pune. Over 40 years of teaching and research experience in national as well as international environment. He is the editor in several reputed journals. A dynamic statistician with over 40 years of rich academic and research-oriented experience in national as well as international environment. Expertise in applications of various statistical packages, namely SAS, S+, R, SPSS, MATLAB, and Minitab for researches and analysis. expertise in web designing using HTML. His recent research area is virality regression models for univariate and bivariate survival data, censoring schemes, Bayesian inference for bivariate survival data, bootstrapping, Monte Carlo methods, MCMC algorithms, and software reliability growth models. In general, his research area is inference in bivariate and multivariate exponential distribution, selection of better component in two-component system, stress strength models, reliability theory, multivariate Pareto and variable distributions, characterization, non-parametric inference, tests for bivariate and multivariate exponentially against positive aging, survival analysis, virality models. In his credit, he is a 10 professional affiliation is attached. Now, I request on behalf of organizing committee, Professor David Hangel, his title of the talk is Modeling Kidney Infection Data Using Compound Geometric Shared Virality Model Based on Additive Hazards. We warm welcome to Professor David Hangel to share your ideas in the latest forum, please.
Okay, thank you for the introduction. Can you hear me?
Yes, Professor.
Yeah, and can you see the screen presentation?
Yeah, it's fine.
All right. All right. I'll just open the screen. Make a big full screen. Can I do full screen?
Yeah, you can make it a full screen, clicking on the either the slideshow or that symbol.
I'll just do this full screen. Okay, anyway. All right. Thank you. The title of my talk is Modeling Kidney Infection Data Using Compound Geometric Shear Variety Models based on additive hazard. This is based on survival data. The survival data has censoring data. It may be right censoring or left censoring. Different types of censoring are there already in the literature. I'm using the right censoring, random censoring. Sensor data, survival data is a time to event data. The event may be either death or some infection or any event that happens. It may not necessarily death, maybe infection or some other things. Okay. It may be in the marriage data, means in the case of marriage, marriage is an event. In the case of employment data, employment is an event, something like that. Okay, it has some sensor data based on the information, whatever, what we can do, the possible analysis in the sensor data. Say, very beginning, I start with the data. I'm just going through. Something happened.
Bottom, the third small that there is a click on that. Now the screen is not in.
Okay, I'm just moving the screen.
Right side from the bottom, third person, you please click.
You can see the presentation screen.
Yeah,
no?
we can see the first page now. Yeah,
I'm just doing the slides.
Yeah, let us. Yeah, okay. Let us try to last the right end from the bottom. There is a minus plus like
Magnifying
that,
glass.
magnifying like that. From above that, there is a slideshow.
I'm just doing
Is
it.
it okay? Otherwise, you can move and can present those.
Maybe I can do it here.
Last right that line by light.
Now we can see.
Yeah, we can see outline.
Okay. All right. First, we present the data, kidney infection data, before going to the analysis part. Okay. The data is having 38 kidney patients total, and there are two infections. Okay. The first kidney and second recurrence time for the first kidney and second kidney, there are two times. It's a bivariate data with censored indicator 0, 1, 0 for the censored and 1 for the recurrence time. And 5 covariates are there. Okay, in all, age, gender, and 3 types of diseases. These diseases, GN, AN, PKD, these are written whether the disease is present or absent. Okay, that is a thing, 0, 1. These are binary. Okay, and gender is 0 for male, 1 for female, and absence or presence of the disease, that is of 3 diseases. In all, there are 5 covariates. Okay, with 38 patients with 5 covariates. This is the data. Okay, what can be done with this data? There are several methods of survival analysis data, Kaplan-Meier estimates, and some Cox regression models given by Cox proportion hazard model given by Cox and other things. All can be done. And what more can be done with this data? Any new models can be applied. Anyway, existing literature is already there. Can we have some new models based on this data? And we have done a new model that is a compound geometric distribution as a variety distribution in this paper. There are earlier models are also there, gamma, inverse Gaussian, positive stable, different variety of distributions already there in the literature. And in this paper, we have some new model that is compound geometric distribution as a variety distribution. In all, there are 38 patients. 23 patients, both recurrence times are observed. 9 patients, first recurrence time is observed. Second recurrence time is censored. Third patient, first recurrence time is censored and the second time is observed. 3 patients, both recurrence times are censored. In all, if you add all these numbers, 23, 9, 3, and 3, it adds to 38 patients. This is the data. Time 1, first recurrence time, the censoring indicator. Time 2, second recurrence time, and the second censoring indicator. Age of the patients, the sex male, female, 0 for male and 1 for female. GN, AN, these are the 3 type of diseases, presence and absence of disease. This is the detailed data. Okay. Survival is, I already explained, time to event data with some censored data in that. I'm using the right censoring data, okay, and the shared variety models. The Cox 1972 has given Cox proportional hazard model, okay, that is given in this equation number 1. ST given X, okay, this is a hazard rate, given X is a covariate, H naught is a baseline hazard, X prime is the explanatory variable, beta is the regression coefficients corresponding to the explanatory variables. This is a model given by Cox and it is well known in the literature. And
it's 11 o'clock.
One of the basic assumption for this model is homogeneity of the subjects of the population, which is somewhat questionable. In reality, the individuals differ substantially from each other in susceptibility to various diseases and morbidity test. No matter how many COVIDs you want to add, it will never be complete one, especially in the case of human studies. Okay, why this variety? What are the reasons? The common reasons for having unmeasured and neglected. Usually, this is a neglected covariate. The variety is an unknown, unmeasured, neglected covariates. These are too many covariates to consider. In that case, we just drop some of the covariates without the knowledge. Lack of appropriate tools to measure the covariate. There are no tools available to measure the covariates, and that's why
Good morning, Professor Kumar. Good morning, Professor.
Yes, sir.
this effect or variety is not directly estimated from the data, but instead is assumed to have unit mean and finite variance, which is to be estimated. Share variety parameter is due to some genetic factor or environmental factors, which are unobserved in an individual and are common and shared by both paired organs in human or twins in the family.
Good morning, everyone, and
This
warm
share
welcome to all of you to
variety
technical session
parameter is
number 11.
also responsible for the dependence between the two components, two or more components, it may be. What happens if you ignore the variety? If the variety is significant in the model and is ignored, then the model will be inappropriate and the decision based on such models is be misleading. If the variety is ignored, the estimates of the regression coefficients will underestimate or overestimate. And the model selection criteria AIC, BIC, DIC will be more as compared to the model with variety. The decision based on the model without variety will go wrong. Ignoring the variety effect with a finite mean may result in a negative bias in the estimated time dependence. In general term, we'll let the heterogeneity go into the error term. This will of course lead to increase in the variability of the response as compared to the case when the variety is included. These are the effect of ignoring the variety models. Some examples of share variety. If we take for example genetic factor, offsprings in the family share the same genetic factor and have similar or common risks. Most of the genes come from their parents and the children share the common risks. There is a common that is called shared priority model. Take for in the case of hospital centers, the patients in the hospital share the common risk because of the same doctors, staff, operation theater, and the environment. So the patients share the common risk. That is a share priority model. These are some examples. The unobserved covariate U, if the priority acts additively on the hazard rate function. In such situation, a univariate priority model is derived as follows. Let a continuous random variable t be lifetime of an individual. The additive hazard model in which covariates act additively on the baseline hazard is given by. That is this function. Okay, that is a addition of this with baseline hazard. In the equation number 1, we have seen instead of this addition, there is a product. That is a multiplicative model. Here, the addition is there. That's why it is called additive hazard model. And I can write Z as e raised to u beta u. U is the unobserved covariate, beta u is the corresponding regression coefficient corresponding to u. That is Z. Z is between 0 to infinity because u is minus infinity to plus infinity. That is, this is a form of additive hazard model, equation number 3. Okay, the cumulative hazard can be obtained as integrating over t, you get this one. And conditional hazard function for a given priority t, you know the relation between survival function and cumulative hazard. Just use a relation, you get this function. H naught t is the cumulative baseline hazard function at time t. Now integrate over the range of the variable z, having the density function z. Taking density function of z is fz, we get the marginal survival function. That is this one. And that is e raised to minus h naught t and L. Lz is a Laplace transformation of the distribution of z. Z is a distribution of the priority random variable. That is the thing. It may be any distribution. It may be either gamma, inverse Gaussian, positive stable, compound Poisson, or compound Poisson geometric distribution. In our paper, it is compound geometric distribution. Okay. If there are two component system, say T1, T2 are the lifetime of the two components, and Z is a priority random variable, and Xi is a observed covariates, and you can obtain here given Z, T1, T2 are independent. When you integrate over Z, this Z is common between two T1, T2, then T1, T2 will become dependent when you integrate over Z. That is this form. And here T1, T2 will be dependent after integration. You can see here, after the integration, the T1, T2 will become dependent. You can't separate it out. Here's T1, T2. Here it is okay, but in case of LZ, you can't separate T1, T2 here. That is the thing. That's why the dependence term will arise in the case of joint survival function. Okay. There are numerous types of priority models in the literature. It is already there in the literature. And in this paper, we are doing the compound geometric. Negative binomial is a submodel of geometric distribution in that case. That is there. Okay. Now, what is compound geometric priority distribution? Allen in 1988 and 1992 introduced compound Poisson distribution as a mixing distribution in survival model, which is the extension of one studied by Hogarth. The compound geometric distribution is similar to compound Poisson distribution, in which mixing distribution is geometric. In place of uh, Poisson distribution, it is geometric distribution. That's why the word compound geometric distribution. Okay, it plays a prominent role in this extension being used here as a mixing distribution, and this distribution has many attractive properties in non-susceptible or zero susceptibility type of data, a convenient variety distribution. Okay, there are some example of non-susceptibility type of data. That means n is greater than 0. See, compound geometric distribution, it has n equal to 0 with positive probability and greater than 0. Okay, you can split into two terms because n equal to 0 has a positive probability. That is zero susceptibility. Okay, we can interpret Z as aggregate heterogeneity due to failures before we get some success can be given as in case of marriage data, Z may be represent heterogeneity due to difficulties in finding the marriageable partner before individual meet first suitable partner. In case of fertility, Z may be heterogeneity due to miscarriages observed or unable to conceive a child with a couple before they have first child. Some others would like to deliver babies until they deliver baby. There are some non-susceptibility type of data that means n is greater than 0. N is greater than 0. Some other example, politicians go on contesting election until they win. Individuals go on changing the jobs until he or she get a suitable job. In such situation, compound geometric distribution is a suitable choice for a variate n. Some individuals have 0. I am giving an example of n equal to 0. Okay, so that they will get succeed at the first attempt without any failures. There are no failures. At very first attempt, they get the success. That is n equal to 0. Infertility case data, no miscarriage observed. Some mothers able to deliver baby boy for their first child. Politician win election at the very first attempt. In unemployed data, individuals get the job. These are the example of n equal to 0. Student pass the exam at the very first attempt. This is the data of susceptibility n equal to 0. There are earlier papers by myself and my students that was for the compound geometric variety distribution to analyze this one. This is not the this is the multiplicative model in the earlier distribution. Okay, the use of compound geometric distribution is not only mathematical convenient but might also seen as natural is more substantial sense. The distribution arises in some of the random variables of independent gamma variables. Okay. There are two distributions involved. One is gamma and another is geometric. Z is written as random sum of this gamma variables. Xi's are gamma variables. N is geometric distribution. That's why it's called compound geometric distribution. Okay. Xi's are iodic gamma with scale parameter nu and shape parameter gamma. And Z has two parts, n equal to 0, that is Z is 0 and Z is greater than 0. This is a susceptibility part. Whenever n is 0, the Z is 0. That is there. And when n is greater than 0, Z is sum of all this. Given n, this is sum of Xi's, sum of IID gamma. Sum of ID gamma is again a gamma with the scale parameter this and shape parameters n gamma. Okay, this is the given n. This is again a gamma distribution. Okay, and n is geometric. That is this one, geometric distribution. Okay, then f of z. Okay, this is a compound geometric distribution. I'm taking both together, n and uh, Poisson, this geometric and this one. This is the PDF. Laplace transform of gamma is this, and Laplace transform of geometric is this one. We need a Laplace transform of compound geometric. That means we have to take both together. The gamma, Laplace transform of gamma as well as Laplace transform of geometric. To go both together combined is here. That is this final form of Laplace transform. This is the final form of compound geometric distribution. Expected of Z and variance of Z. In order to resolve non-identity problem in the variety distributions, we take expected value of Z equal to 1 in this. And there will be some restriction on the parameters when you take expected of Z equal to 1. That is this restriction. P nu equal to Q gamma. Q is and regression coefficient as normal prior. Okay. These are the MCMC techniques, Gibbs sample we have used for this simulation study. Okay. We have taken some hyperparameters for A1, A2, B1, B2. Okay. We have fixed all these hyperparameters. One can change the hyperparameters also, but it won't make much difference. We use two tests. One is Geveke test for this MCMC techniques. Okay. And another is Gelman-Rubin. This is whether the chains converge or not. To test that, we use Geveke test and Gelman-Rubin test. That is the thing. That is. And we have table 1 and table 2 for the simulation study. Okay, this table 1 is a baseline distribution for log logistic distribution with compound. The estimates are very close to the true value of the parameters. Okay, the standard error, lower credible limits, upper credible limits, Geveke values, and the p values. Okay, p values are very close to 1. Okay, yes, the convergence has been reached. Gelman-Rubin values are close to 1. That means the convergence has achieved. Okay, for the chains. And similarly for the second one, using the compound, the generalized variable as a baseline. Okay, that is model 3. Here also we get the same situation. The estimates are close, standard error and this one. Kidney infection data, 38 patients with 5 covariates, already described earlier. This is the model we have used with 5 covariates, okay, with additive hazard. Some tables, case statistics, p-values of the case statistics, they are very high, then they are very close to the assumed model. That means whatever we assumed in the model are the goodness of it for the test is good for this model. Therefore, the data came from these models. Posterior summary of these parameters estimates standard error, lower and upper variables. What we see here is beta 2 is negative and both lower and upper credible limits, they are negative. The also significant. Okay. Okay. These two are significant. All other are not that significant. These two are significant. That means beta 2 is gender effect. That means females have lower risk of infection as compared to male counterparts. Okay. The absence of the disease type 3 have a lower infection as compared to the presence of the disease. That is the interpretation. This is for model 1. Model 2 is also the same thing. It's both lower and upper are negative, therefore it is significant. Model 3, here also you can see the same. The chains, from this we can conclude that the MCMC chains are convergent. This is for model 3, model 4 also same. In all these cases, all 4 models, what we observe is the females have the lower risk of infection, the kidney infection, as counterpart. Now, which model out of these 4? From that, we can have the model selection criteria, okay, AIC, BIC, DIC. Okay, whichever is having the least value of AIC, BIC, DIC, that is a better model. Compound geometric as a baseline, okay. Compound geometric as a priority and generalized Rogers as this one. And what you see here, the model 3 is the least one. This is also least, this is also least, this is also least. Okay. The generalized Weibull distribution as a baseline and compound geometric as a priority. That is the least one. Next comes the model 1, then model 2 and 4, because they are without priority. The base factor also tells the same. Model 3 is always better than the model 1. Yeah, that is there. Model 3 is always better. Model 3 is better than model 1. Model 3 is better than 2. Model 3 is better than 5. That means it's better than all other 3 models. Strong. I'm comparing with the existing models in the literature, in the earlier literature. What we see here is model 3 is better than all other models, previous models. It's least in all AIC, BIC, and DIC. Okay, that is there. Next one is the model 1. This one that is equal to 47 for model 1, model 3, and 52 for the model 1. This is very high value. Sigma square is very high. Therefore, there is a heterogeneity factor is significant. Therefore, we have to use priority models. There is no point in testing sigma square equal to 0 because it's very high value. Okay. Next is, okay, AIC BAC values. Okay, comparison between the 4 models. The models with priority having the lower risk, and the priority models fit better than without priority model. The smallest is model 3. The smallest values of AIC BIC is model 3. Generalized Weibull distribution with priority is better than other 3 models. The same case with the Bayesian test, that is a base factor. What we conclude here is the shear priority compound geometric priority with generalized Weibull as a baseline distribution fits better than other models for analyzing the kidney infection data. Okay, from the table 10, the compound geometric priority model based on additive hazard model are better than the existing additive hazard models. Okay. Okay, thank you. This is the end of this presentation. And I have used only the baseline model as 2 models. One can have different baseline models also, and one can also have non-parametric baseline models. In that case, we can get semi-parametric models because the baseline model is non-parametric. We have semi-parametric models. One can have also judged as a process, okay, stochastic process. Okay, that is also possible with some stochastic process as a judged as a stochastic random variable process or something, inverse Gaussian process, different types of Weibull process and other things. These are also possible in the literature. Whatever we did here is based on the kidney infection data. And if you use some other data, some other model may be better in that case. Okay, that is the thing. Okay, thank you.
Thank you, Professor David Hangal. You have your valuable time. You spend a valuable time for this great platform. Once again, I wish to express heartfelt thanks for the Professor David Hangal. Now, due to time short, I can invite 1 or 2 researchers, those who are interested to interact with Professor David Hangal. Just 1 or 2 queries only, please. If no query, let us thank Professor David Hangal for giving the wonderful presentation to the great platform. Thank you very much. Thank you very much.
Thank you very much.
Now, I wish to express my heartfelt thanks and the blessings to Professor Satish and his team for conducting a good platform for all researchers. Thank you, Professor Satish and his team. Thank you very much. Mr. Satish? Or any of the organizing team members?
Yes, sir. Thank you.
Please, madam. Thank you. Yeah, you can give on behalf of organizing committee. You can give word of thanks. Then come to the next session, please. Professor Satish is coming. Thank you very much, Professor Satish.
Thank you, Satish. Thank you for inviting me and having a valuable and useful lectures. I also attended. Thank you for all.
Professor Satish, thank you very much.
Yes. Thank you, Professor. Thank you.
Thank you. My hearty wishes and congratulations for the great achievement you achieved. Thank you.
Thank you, Professor. Thank you so much.
Thank you very much.
Since the other platforms are also going on, there's a slight network problem. That's why. Sorry. We are thankful to you,
Dr.
and we
Harigal.
are always thankful to you, Process, for your support. Yeah.
Sunadhan, Professor Harigal, nice talk. Enjoy.
Thank you, Professor Sendamarakannan sir.
Thank you very
It's a
much, sir.
wonderful event going together with your able comments and coordination. Thank you very much.
Thank you. Satish Kumar, can you hear me?
Amna?
You can hear me? Am I audible?
Yes, Professor Rao, you are audible.
I'm audible.
Yeah, we can hear you, Rao.
Thank you. Because
Yes.
tomorrow I have a lecture.
Yeah.
I want to
Yes.
make sure that I'm audible.
Yes.
Okay.
Yeah.
Thank you.
Uh, Thank you, Professor Hanagal.
Professor Hanagal has left, it
Yeah.
seems.
You know, I am here.
Yeah,
Okay.
no.
Yeah.
Yeah. Thank you.
Professor, it was a very great lecture, starting from the scratch and gradually building towards the very peak of the combinations of all comparisons. It's really wonderful, enjoyable, and it's like anything to say. I really speak like anything.
Thank you.
Thank you, Professor.
Thank you.
Devika, whether you concluded and
Yes, I did. Thank you. On behalf of the organizing committee of WSTA 2026, I extend my sincere gratitude to our session chair, Professor Sendamare Kannan, for his valuable guidance and for chairing this technical session so effectively. I express my heartfelt thanks to our distinguished speakers, Professor Carlos Coelho and Professor David Hanagal, for their excellent presentations and for sharing their valuable research and insights with us. I also extend my sincere appreciation to all the participants for your enthusiastic presence, active participation, and engaging interactions, which greatly contributed to the success of the section. Once again, thank you all for being a part of this wonderful session. Thank you.
Thank you all. Thank you all.
Amrita, you can initiate the next session. Please.
Good morning, everyone. A very warm welcome to all of you to the 12th technical section, a special invited section of the WSTA 2026, 11th International Webinar on Recent Trends in Statistical Theory and its Applications. It's my pleasure to introduce our session chair, Professor Ismail B., Professor and Head of Department of Statistics, Yenapoya, Mangalore, and former Professor and Chairman of the Department of Postgraduate Studies and Research in Statistics, Mangalore University. He is a distinguished statistician with significant contribution to regression analysis, econometrics, and statistical modeling. Today, we are honored to have three eminent speakers in this section. Our first invited speaker is Dr. Martin Luther William from the Loyola College, Chennai. His research interests include regression modeling, multicollinearity, and applied statistical methods. He has contributed extensively to statistical research and teaching. Our second invited speaker is Professor Rahul Gupta from the University of Jammu, with over 3 decades of experience in teaching and research. He specializes in statistical inference and made a significant contribution to higher education and statistical research. Our third invited speaker is Professor K.K. Jose from MG University, Kottayam. A renowned statistician and academic leader, his research focuses on stochastic modeling, statistical inference, and applied statistics. We are delighted to have our distinguished chair and invited speakers with us today. I now respectfully invite Professor Ismail B. to kindly chair the session and commence the proceedings. Over to you, sir.
Thank you, Amrita. Good morning to you all. At the outset, let me congratulate Professor Satish for organizing this WSTA 2026 successful series of international conferences. Now, without taking much time, let me invite Dr. Martin Luther William and his ideas to the gathering. And before giving the presentation, let me take an opportunity to give a brief introduction of Martin Luther William. He's a retired associate professor and head of the department at Loyola College, Chennai. Loyola College is a pioneer institution in statistical sciences with the stalwarts like Dore Rajan sir and Chandrasekhar sir. Martin Luther, also a 100% product of Loyola, did his UG, PG, MPhil, PhD at Loyola College. He had got a teaching experience of 37.5 years, a very lengthy service in teaching as a teacher. He taught a wide array of subjects in all levels, UG, PG, and MPhil, specialized in encouraging MSc students to do mini projects as part of their continuous assessment in papers in like regression analysis, categorical data analysis, multivariate analysis, testing of hypotheses, non-parametric methods, which includes most of the core areas of statistics. He has 31 research publications in national and international journals and in conference proceedings. He has successfully guided 5 scholars for PhD degree, and his area of research interest already mentioned, regression analysis, multivariate analysis, statistical inference, distribution theory, and statistical computing. And he's participated in several national and international conferences to present contributory papers and also delivered invited talks in several academic conferences. Industrial consulting experience in data analytics for more than 15 years, guided real-time analytical projects as visiting consultant for analytical companies in the different areas, including statistical software development, customer training, customer human resource management, etc. And he has many other lengthy other activities, which I don't want to spend time on that. And with this brief introduction, let me invite Dr. Martin Luther William to this international conference to deliver the invited speak. Over to you, sir.
Welcome.
Hello.
You are most welcome for this conference, and I request you to present your talk. You have 30 minutes and 5 minutes for discussion. Totally 35 minutes.
Yes, sir. Very good morning, Professor Ismail, sir. Thank you so much for the words of introduction to me. I hope I am audible.
Yes, sir. You are clear.
Yeah.
We can hear, sir. It is clear.
Thank God Almighty for the day. Thank you, sir. Praise to the Lord Almighty for this day. And at the very outset, I greet every one of you for assembling here to attend this conference. Especially, I would like to thank Professor Satish Kumar for his untiring efforts to bring statisticians onto a single platform. He has been doing it consistently every year, twice every year, and many times I'm not able to attend, but this time, thank God that I'm able to attend this conference. Thank you, Professor Satish and his team. And I'll directly go to the topic of my presentation here.
Presentation വരുന്നില്ലല്ലോ.
Yeah. Are you giving the presentation? It's not seen, Professor. Your slides are not seen.
Not visible.
Not visible as also is not in. Yeah.
It's better to share it once again.
Yeah. Please share once again.
Hello.
Hello. We can't see your slides.
Yeah.
It's not visible.
Yeah, there was a net problem, I think, sir. There was an internet connectivity issue.
Okay.
Sorry. Yeah. Yeah, I'll present it now.
Okay.
Hope the screen is visible to everyone. So the topic of my presentation here is resolution of collinearity through location shift and partial regression splines with an application to crime data modeling. In linear regression, collinearity means the presence of undesirable levels of correlation between the predictor variables, or what we call the independent variables, to the extent of affecting the way in which their relationship to the response variable is expressed. When predictor variables are correlated, their slope coefficients cannot independently explain their effects on the dependent variable. In other words, the part of the variation in the response variable explained by one variable gets confounded with the other variables, and the statistical significances are reduced. The ill effects of collinearity have been discussed to a good extent in the excellent text of Montgomery, and there are several research papers over the years which have addressed this issue of multicollinearity. Farrar and Glauber, 1967 onwards. We have so many references, Mela and Coppelate, 2002, besides many others. The publishing of articles and the continuing interest on the issue of spline shift combination has the do not come into the